Hello everybody, this is our solar heating project. I'm Brewster, and then my partners are Danny and Ollie, so we'll be talking a little bit about our process in going through this project. So some of our objectives when we're completing this project, we knew it had to be a solar energy, so the energy that went into the system had to be produced from solar heat, either be it radiation or electricity produced from solar panels, photovoltaically. We knew that for the project, the requirement was to have 50% of the energy generated per year eliminated. So this project would result in zero cost energy for half of a home's general heating requirement across an entire year. After we finish this, the end goal is to perform an economic analysis based on how much money we would save and how long it would take to recuperate the amount of money that we inputted or invested into the project. So that's the general overview of the project, and my partners will give you a little bit more in depth onto how we started and how we really attacked this problem.
All right, so our original project design here involved the solar energy from the sun being introduced to the solar panels, which then just through wiring made it to our conventional electric heater, and from there that would produce the hot air required to heat 50% of the house. We kind of just ended up making a more in-depth design digitally on our second deliverable, and this just gives you a good idea of the cold air and hot air circulation involved. We have also introduced a battery that's 40 kilowatt hours. Originally we had planned for 20 kilowatt hours, but we had to implement a larger battery because we knew we had to store just around 40 kilowatt hours of energy for night times when the solar panels would be taking energy.
After we got our conceptual design, we first started working on our calculations. So to find we first found the volumetric flow rate and mass flow rate. We did this by taking a few assumptions. So first we found the median home size in Pennsylvania, according to the Federal Reserve, to be about 1,700 square feet, and the average height of ceilings in an American residential home would be 8 feet. So doing simple calculations, we found the volume of the house to be 13,000 square feet, or about just under 400 cubic meters. And then, according to the American Lung Association, HVAC systems should cycle air at least 0.3 times an hour, which equates to about 2.8 hours for each air change. Using that math, we could find the volumetric flow rates to be about 135 meters cubed an hour, or 0.037 meters cubed per second. And then using our assumed temperature to be 70 degrees inside the house, we found the density of air to be 1.198 kilograms per meter squared. And from that, we were able to find the mass flow rate to be 162 kilograms per hour, or 0.045 kilograms per second.
All right, so just to get a good idea of some of the heat loss that would be lost due to conduction, we did some calculations on the basis of assuming that this is a perfectly square house. So we were able to calculate both the wall space and ceiling space, as well as the floor space that could potentially lose energy that's being from the heat that's being circulated through the house. So we have 332.7 square meters squared of area for this heat to be lost to, and with an outside temperature of 21.1 degrees, or an inside temperature of 21.1 degrees Celsius, and an assumed outside temperature of -2 degrees Celsius, which is the average temperature in Pennsylvania during January for the winter, when we're really going to need this heating system to be working well. We have a Q loss from conduction of 3.65 kilowatts, and in addition to that, we calculated the heat loss due to circulated air, which is the next slide.
So, taking into account all the different possibilities and really analyzing every part of this system was what we did. And we knew that in terms of the equation, the house loses a bunch of heat, it radiates heat out, and that's what Danny was just talking about, the conduction, the Q loss of conduction. But another part of the system that requires heat energy is the air that's circulating throughout the house. We know that, so that's what we call Q of the ventilation. And we know that 0.045 kilograms per second of air is coming into the system, and we need to heat that air into the proper temperature to a 21.1 degrees Celsius. So we calculated the energy required, or the Q dot required to heat this ventilated air to be 1.09 kilowatts. And then we added the Q dot of the conduction and the Q dot of the ventilation to find the total loss of heat energy in the system, which we determined to be 4.74 kilowatts per day, which we then basically said, we know that the internal energy of the system we don't want to change. So Q in is equal to Q out, and the amount of energy that we need to input into the system is the same as the amount of energy that leaves it.
All right, so since we found the total heating that we need to be, which is 4.74 kilowatts, and over a day that'd be about 113 kilowatt hours. So we determined for 50% efficiency, we wanted 56.8 kilowatt hours of solar energy every day, which is 50% of the heating demand. So using solar radiation found from the National Solar Radiation Database, we found the clear sky GHI, which is used to determine the watts per meter squared from solar radiation. We found the average day and night to be just under 130 watts per meter squared. So assuming a 20% efficiency, which is standard according to the National Renewable Energy Laboratory, and assuming there were no other losses from the wiring, since they're so small it'd be negligible, and a battery, we assumed any losses from the battery would just be converted into heat into the house, which is where we want the heat. We solved for the roof space required, covered in PV panels in order to generate that goal of the 56 kilowatt hours. We found that to be about 91.2 meters squared, or about 1,000 square feet. And then using the standard residential panel square footage, which is about 17.5 square feet, we required at least 58 PV panels to achieve our goal.
So this is where we really dived into an analysis of the old system that we were using beforehand and the new system that we have implemented. So remember, we implemented a bunch of solar panels and also a new heater. So the old system, we knew that we're using 9.5 hours of sunlight per day, for the peak hours that the electricity company is charging the most money is from 2 p.m. to 9 p.m. So we're going to use that to our advantage. During non-peak hours, electricity costs 11.8 cents per kilowatt hour. During peak hours, this is 20.15 cents per kilowatt hour. So we really want to minimize the amount of time that we are using electricity during the peak hours. Did some little basic calculations to find how much money we spent in a day for the old system, and that came out to be around $16 a day for heating energy, which is a little surprising, you would think. And we converted to the new system. So for the new system, we took a little different of an approach. During the light of the day hours, the solar panels are producing enough energy to actually sustain the house and its energy required to power the heating without having to pay any money to the grid or to the power company. And there's also an excess energy. So we take that small excess energy, which is 1.28 kilowatt hours of sunlight, and multiply that by the 9.5 hours that the sun is out during the day, which gives us right about 12.21 kilowatt hours that's going into the battery. Now this energy comes out of the battery during the nighttime and further reduces the amount of electricity that we use. We calculated that the total amount saved based off of these 9.5 hours of the solar panel running is actually going to be saving $9.50 per day, and this is 59% of the electricity. So it definitely fits the project requirements for this project specifically.
All right, now to the ventilation specs. So earlier we found the VDOT, the volumetric flow rate. We found that to be about 0.037 meters cubed per second, or about 37.7 liters per second. This means that we would need an HVAC system, a circulation pump, that circulates at least 50 liters per second to be safe in order to, for some peak hours where we might need more. Since it's an air-based system, we can use normal traditional ducting materials such as aluminum. According to engineering toolbox, for a residential home that has ventilation needs of less than 1,000 meters cubed per second or per hour, the velocity of the air is 3 meters per second. So using that, we can solve for the cross-sectional area of the main duct, which will take the heat from the electric furnace and spread it out throughout the house to be about 0.11 meters squared, or a minimum ducting cross-sectional area of 1.25 feet squared.
So a good question to ask about an energy system is always the return on investment, and this is basically just involving how much money is going to be saved and how much money is going to be spent originally, and how long it might take for this system to pay off, because not only should it be energy efficient, but it should also be cost efficient. So using the our previous measure of $9.50 a day saved, when comparing that, multiplied over a year, that would be about $3,500 a year that's going to be saved. And with the total cost between the solar panels, the air circulation pump, and the battery cost, that comes out at about $75,800. So just comparing these two numbers, it would take about 21.7 years for this system to pay itself off when compared to our old system.
That concludes our presentation.
Thank you very much.
Thank you for watching.
There's so much.
All right, Pledge.
That's 14 minutes, guys.